So, our next contour integral is the integral of sine of z over z times z squared plus 1 dz from minus infinity to infinity. Actually, I think it was there with an x, but it's pretty much the same to do with a z. Now, the standard way of doing integrals like this is to take a contour like this and to integrate this function around the contour. Then one tries to show that the integral around the circular arc part of the contour goes to 0. Now, that works very well if we've got an exponential here, but if we've got a sine x here, then in this direction we've got a hyperbolic sine of the y variable, and that suggests that, say, at this point here, the value of this is actually growing exponentially with the r. It's certainly not going to 0. And that's going to make it very hard to apply the ML lemma to show that this is going to 0. And we can't apply Jordan's lemma because, we can't apply Jordan's lemma because that's about an e to the iz. However, we can notice that this is equal to the imaginary part of the integral from minus infinity to infinity of e to the iz over z squared plus 1 dz. If I take the imaginary part, well, when z's a real number, this is real, but this is a cos z plus I sine z. When I take the imaginary part, I just pick up the sine z bit. So the question is now, how can we do this integral? Now, making the change to this integral is good in the sense that this is the kind of integral where in the upper half plane, e to the iz in modulus is less than or equal to 1, and here's something that on this arc of the circle of radius r, this is going to look like roughly like 1 over r cubed, and so that's going to work very well for the ML lemma. But notice now that in doing this, we have a problem because when z is equal to 0, which is a point on the axis, then here we've got something that's looking like 1 over z, which is a pretty nasty integral. So we have to cheat a little bit and put in a little indent. So we've got a large circle of radius r and a small circle of radius little r. So this is now the contour that we're going to integrate around. When I integrate around this contour, assuming that r is less than 1 and that big R is greater than 1, when I integrate around this contour, I have to look, the residue theorem will tell me that the integral around the contour is equal to 2 pi I times the sum of the residues, so I have to look to see where the singularities are, and I see that there is a singularity inside here at I. And that's the only singularity. There's a singularity at 0, and there's a singularity at minus I, but they're outside the contour. So I can integrate around that contour, and it's not too hard to find the residue when z is equal to I of that. So we can find the residue and deal with that part of the integral. Now, I'm going to write this bit as being A, B, C, D, alpha, beta, gamma, and delta. The integral over alpha, for simplicity, I'll call that f of z dz plus the integral over gamma of f of z dz. These are going to be integrals from minus capital R to minus little r and from little r to big R. These are not going to be quite this integral here, but it will be true that the limit when little r goes to 0 and big R goes to infinity of this is the integral that we want. So that bit's okay. It's also going to be true that on the big arc, this tends to 0, and the argument is by the ML lemma. And essentially, the key to that is just that the modulus of f of z is less than or equal to 1 over r squared minus 1 on delta, on that arc delta. So this, here is my m. If I multiply by L, which is pi r, I've still got an r in the denominator. I've got an r squared in the denominator to go to 0. So these ones are okay, this one's okay. The tricky one is the integral over beta. So this is tending to 0 as r goes to infinity. What do we have to do about this bit here? Well, there's not much we can do here except actually write it down. So for this little bit of the contour, I'm going to observe that I can take z equals little r e to the I theta. Well, as I go around the contour, theta is actually going from pi down to 0. So theta from pi to 0. And when I write z like this, then I get that dz by d theta is equal to I r e to the I theta, which is the same thing as I times z. When I sub in all of these things, then I will get an integral from minus pi to 0 of e to the I times r e times e to the I theta over this z is going to go with the dz. It's like saying dz over z is equal to I times d theta, and then I've got z squared plus 1, which is r e to the I theta squared plus 1. Now, this is an integral that, to put it mildly, is pretty horrible. We can't really hope to do this. But, for once, limits are actually our friend rather than our enemy. If I were to stick in here the limit as r goes to 0 of this, then I can stick this in here. And if I appeal to the theorem about when it is that I can put a limit inside an integral, I can see that when r is a very small number, say if r is less than 1/10, then this, first of all, depends continuously on r and theta, and also it's uniformly bounded. If you like, you can say mod f of z is less than or equal to something that depends on, it's going to be like a 1 minus r squared, basically. 1 over 1 minus r squared. So we're able to apply the theorem that says I can put the limit inside, and so this is equal to integral from minus pi to 0. Now I put the limit inside. I've got the same thing here, e to the I, r, e to the I theta, d theta, actually I d theta, over r e to the I theta squared plus 1. When r goes to 0, this becomes e to the 0, which is 1. This becomes 0. that stays 1. So I have interval from minus pi to 0, I d theta, and that is equal to I, sorry, that's not minus pi, this should be pi, this should be pi, this should be pi, because the argument is going down from pi down to 0. So it's pi, 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 and this is equal to minus I pi. So at this point, at least when little r goes to 0 and big R goes to infinity, I know exactly what happens to all of these things. And these ingredients, together with the residue theorem, are enough to solve this problem.